In the next demo, I will present a spike that we've done, and that is deep reinforcement learning in the resolution process. So let me share my screen, and I prepared a few slides just to give an overview. So as of now, we are using gradient-free methods, that is temporal difference learning and Monte Carlo tree search, or Monte Carlo tree learning during the resolution process. So we know how to resolve software stacks that have high quality given data and observations that we have. But what if we plug a deep reinforcement learning algorithm? So let's take a look at gradient methods and how they could be utilized during the resolution process. Just to give some context here, you probably already know this plot, but basically what we are doing, we are scoring software stacks. So if a software stack is made out of two libraries, one is called simplib and the other one is another lib, and we switch versions of these libraries and score them, we can get this interpolated surface that states scores when some specific version of simplib and some specific version of another lib is used. In Thoth, we are looking for software stacks that have high quality when recommending software stacks. So we are interested in these spikes we would like to see in resolved software stacks. Now, let's try to build a model that will guide the resolution process using gradient methods. In that case, it will guide the resolution process so that the resolved software stack has high score. There were a few issues, and these issues had to be tackled in order to come up with some solution. So we already know that the state space is quite large. We have a lot of possibilities how to resolve software stacks in different versions. And one of the main issues is that we don't know how big the resolution process is, or how big the state space that is considered is. You can take an example that if you provide TensorFlow as a dependency, then you don't know how many dependencies of TensorFlow can occur. So it can be, I don't know, NumPy in different versions and stuff like that. And you need to also consider version range specifications. To tackle this issue, we introduced a solution that is obtaining resolution, so basically sampling the state space and obtaining trajectories that correspond to resolutions, valid resolutions to software stacks. And these resolutions were kept in a replay buffer that was subsequently used to train a neural network. And this neural network was built during the resolution process and was basically created on the fly based on the sampled data during exploration. This is implementation that corresponds to a proposal from 2018, that is stack quality evaluation. So if you are interested in it, feel free to follow that document. But basically what we do, we are trying to build a model that will guide us through the resolution process. So it will guide us to find high quality software stacks. The model is designed in a way that it accepts some input vector that corresponds to packages and predicts a score that corresponds to cumulative rewards that can be obtained when following the model predictions. We designed states to vec that corresponds to the input vector. So the dots you saw, A1, B1, C1, D1, E1, corresponds to packages that can occur in the software stack. So an example can be the first dot being Flask application, and values that are valid for this input are 0 if Flask does not occur in the software stack, 1 for Flask in version 0.6, 2.2 for Flask in version 0.7 and so on. The other node corresponds to Werkzeug, again in different versions, and 0 if the given package does not occur in the stack. So as you can see, the package can occur in the software stack, but it's not necessarily in there. An example can be TensorBoard that wasn't dependency of TensorFlow, but now it is. Then there is one special node that is a sync node, and that corresponds to a package that was not seen during exploration. So if the exploration phase did not found the given package, there was no input node created for that, and in that case, there is created sync node, and that sync node is used during predictions. So as you can see, these input nodes have assigned packages, and then we have a regression where we predict what will be the score if we take some path. Now, just on the architecture, this architecture was kind of similar to deep Q networks, but in deep Q networks we have classification. So we have some input nodes that go to classification, and that classification basically corresponds to action that should be taken in order to obtain better cumulative rewards. This cannot be directly done in the network that we use because we don't know how the state space looks like, and we basically created that input vector for regression. On the implementation side, then we iterate over all the possible actions that can be taken given the state we are in, and try to predict the cumulative reward using the neural network. So an example can be a state in the resolution where we have Flask in version 0.6, and unresolved dependencies are Werkzeug and TensorFlow. So what we can do, we can ask a neural network what will be the predicted cumulative reward if we consider Werkzeug in version 0.1 in the process, and the neural network will answer. Another use case can be, or the other possible resolution path can be Werkzeug in 0.2, and again the neural network will respond with some prediction on the cumulative reward. As you can see, we have also TensorFlow as an unresolved dependency, and it basically is the same thing. So as an input we provide Flask in 0.6, and we are asking if we add TensorFlow in version 2.3, what will be the cumulative reward predicted. The experiment was taken using mocked data, and these mocked data did not cover dependencies on packages. So the mocked data did not include if I use package X together with package Y, what will be the expected cumulative reward, but rather it was really like mock data, so a linear combination of input features would be, let's say, sufficient. You can see it also on the model loss, where the loss drastically drops over time, and then it does not change that much over epochs. The outcome of this experiment is that as of now we don't have enough data, so we need to collect more observations for packages, and we need to obtain more these causality observations on packages. Like if I have package X and I include Y, and there is some dependency between X and Y that affects my software stack, then a neural network will be a nice approach because it can learn it can train on these patterns that can occur in the state space. Also, we have sparse data. A lot of times there are no changes on score. So if we collect more and more knowledge, then we would probably have better neural networks. I used Open Data Hub for training the neural network, and as was seen, GPU can be beneficial because it requires, or the neural network training is quite exhaustive task, even though the neural network is quite small, as we will see. So gradient-free methods might be good solution for now, at least to collect more data and to provide recommendations. Another interesting thing is that we don't have architecture of the neural network before the resolution process, so we don't know how many inputs to the neural network will we need. So this opens some questions like meta-programming of neural network architecture layer, and we cannot optimize these neural networks before the resolution process if we design the resolution process as discussed. So the outcome now is let's wait with deep reinforcement learning and let's stick with gradient-free methods. But for future ourselves, let's put some notes. Here, an interesting idea could be combining deep reinforcement learning with TD learning or Monte Carlo tree learning, where we would pre-train neural networks for certain subgraphs of dependency graphs. And in that case, we can, for example, pre-train a neural network for TensorFlow and its dependencies, and have different models for security and performance. So this would guide resolution process for some subgraphs, and the other parts of the software stack could be resolved using TD learning and Monte Carlo tree search. We are ready from code side for this. It just introduces more complicated predictor implementation, but we need to have more observations and more data. Now I will show you the actual implementation that I think is quite straightforward. So what I did, I implemented a new predictor that is a neural network, and it's quite easy to read the run method. So if we are in the exploration phase, we randomly sample the state space, so where we basically collect samples that are subsequently used for training the neural network. And then what we do, we train the neural network. So once the exploration phase ends, we shuffle samples that were obtained during this exploration phase, and then we train a neural network that will be trained over some epochs and used subsequently to give recommendations. Now a quick demo. So what I'm requesting to run advisor and create hopefully I can zoom in, and run advisor that is just Flask with any version, and I asked to receive 50,000 or score 50,000 software stacks using our neural network. And in that case, you can see that the pipeline is resolving software stacks in the exploration phase. In this case, we are resolving up to 2,000 stacks per second. So that's an important observation. And here you can see that neural network has two dense layers, and the input shape for that neural networks has 7 nodes. And here you can see training of the neural network. I don't have GPU, so it's CPU-based training. And as you can see, it takes some time. consider that during this time we would score more than 2,000 stacks per second. So you can see that the brute force attack to this state space exploration and state space sampling is much better when we consider 2D learning or Monte Carlo tree learning. I prepared also a Jupyter notebook that was used on Open Data Hub cluster, and that basically uses the same code but uses GPU for training. And again, you can see that took up to 12 minutes to train neural network on 100 epochs. That was just a sample I used, and it used 10,000 samples that were split into train set and validation set, and validation set was 20%. So here you can see results. So as stated before, I think we should stick with gradient-free methods for now, and once we obtain more data, we can then experiment with deep reinforcement learning. And I think having pre-trained models for subgraphs in a dependency graph could be a good option to take. Do you have any questions? If not, thank you for your attention.
One
Yes?
question. Just before, because I probably not inspired you to stick to the gradient methods.
So given the time that is required to train a neural network on the fly during the resolution process, and given the fact that we want to be responsive with requests to the recommendation engine, it could be better to stick with gradient-free methods and explore as much as possible using these gradient-free methods than training a neural network that will require some time, and especially the fact that we don't have yet data to train a neural network.
So the gradient-free methods are in theory or practically faster than gradient methods, right?
For our use case now, yes.
Okay.
Any other question? If not, thanks for your attention.